So welcome to the MAFTEC tutorial. So it's a tutorial about planning aspects for multi-agents. So MAFTEC means multi-agents, flexible, temporal, epistemic, contingent. And so this tutorial is divided in 3 parts. So I will take the first part about epistemic logic, dynamic epistemic logic, and epistemic planning. The second part will be done by Aurélie Beynier about decentralized POM-DPs. And the last part will be taken by Frédéric about temporal planning. Okay, so I suggest to start the first part. So first I will talk about epistemic logic, then dynamic epistemic logic, and then epistemic planning. So the thing is that interaction between different agents rely on knowledge, because the agents do not have the full information about the current state of the world, and especially they take decisions respect to their knowledge. So for instance, if I know that a given place is safe, then I may decide to go there. If I know that you are at the marketplace, I decide to join you. If I know that it's safe, and also you can have higher order knowledge. So for instance, if I know you don't know it's safe, then I decide to tell you that this place is safe. And other examples here involving a higher order knowledge. So if I know you know it's safe, I decide not to tell you because you are already aware that it's safe. And the degree of nesting can be arbitrary. So for instance, you can have a nesting of 3. If I know you know I know it's safe or not, I will not wait for a message for you, so I can do use my energy to do other things. There is a need to build understandable, explainable multi-agent systems. So robots that can interact with humans, and we need to understand the behavior of the robots, especially in case of when there is a failure, and maybe for legal issues and so on. So we do not want to have obscure explanation. So for instance, a robot that has decided to turn left because some variables were satisfied some constraints, or because some neurons in your neural network was activated or not. But we want also to have explanation in terms of knowledge, because it explains the interaction between the different agents of the system. So as here, he decided to turn left because the robot knew that this area was not explored. So the solution that we will talk in this first part will be to reason about knowledge. So especially we want to solve this kind of problem. So given what the agents are sensing about the world, and also given the different actions that were occurred. So actions can be either real actions, like you move things in the world, you change the world, or communication actions. Then you want to infer what each different agent know about the world, and also about others. So what an agent can know about the knowledge of other agents. So here are some references that I used to build this first part, and that you can look afterwards. Okay. I want to thank a former PhD student of mine, Tristan Charrier, who actually many results that will be presented is of him. People from Caen that participated to the implementation of Intiga's world. Sophie Pinchina, who is the head of the Logica group in Rennes, where I'm working actually, and other colleagues. So the list is not exhaustive, but other colleagues with whom I have worked. Okay, so this first part will be divided. First, I will talk about a project that we developed in Rennes called Intiga's world. Then I will tackle quickly epistemic logic, model checking, and theorem proving. So here, I don't know if I will make a very long part about it, but we will see. And then the second part will be about dynamic epistemic logic and epistemic plan. So what is in Tika's world? Actually, it was difficult for me to explain epistemic logic to people. And it was 10 years ago when I tried to explain epistemic logic to other researchers, and especially researchers in logic, AI, and verification, and so on. They had difficulties to understand this type of graph that are cryptostructures. So here you have a world where P is false, another world in which P is true, and the agent does not distinguish whether P is true or false. And it was difficult for them to really understand this type of graph. And that's why we developed a tool where these structures are depicted by comics. So here you have a screenshot of the tool. So you have agents like this. And when you click on an agent, it opens a bubble like this, which contains the possible worlds that this agent is considering. So for instance, this red agent is considering two possible worlds. So this is the picture of the so-called the muddy children puzzle. So it's maybe I can show you in real. So Hintike's world is like this. So you enter into the tool, and then you have many examples. And this is the example, the muddy children with two agents. Here you have a lot of different other examples that you can look. So if I enter into this example, you have here the two agents. So actually they are muddy, but they don't know that they are muddy. Actually, the red agent, for instance, does not know whether he is muddy or not. So maybe he is clean or maybe he is muddy. But he sees the other agents, that's the blue agents, that's so he knows the state of the other agents, and the blue agent is muddy. And it's higher. It captures higher order knowledge, so you can click also on the blue agent here, for instance, and this means that the red agents imagine a world in which he is clean, while the blue agent is muddy, and the blue agent herself, imagines two possible worlds in which she is clean or she is muddy, and so on. And here on the right part, you see the epistemic state, which is the cryptostructure that corresponds to this this situation. So you have sorry, I have sometimes difficulties to close. Well, anyway, so here you have the real world where they are both muddy, which is here, this point, right? And here, for instance, if you click on the blue agents, you have two possible worlds, which are when you take here the blue edge like this. So actually, the current world is possible for agent blue, which is this one. This is just a copy of this one, or it is exactly this one. And here you have another possible world reached from the real one, where only A is muddy, right? And this corresponds to this world. And from this one, when you continue taking the red edges, you will draw the possible worlds of agent red in this already possible world for agent blue. So I hope it's clear. Do you understand, or it's okay? Do you hear me?
Yes, we can hear.
Ah, okay. Okay, so it's like this. So the semantics of knowledge is an agent A knows a property if that property is true in all possible worlds, and and that's it. So actually, the comics does not correspond exactly to the cryptostructure, but corresponds to the unraveling of the cryptostructure, because here the possible world here is duplicated. This one is duplicated here, and so on. So it corresponds to a tree unraveling of the cryptostructure from the real world. And the motivation was to actually also build many examples in the tool that comes from different community. So for instance, you have the example of Sally and Anne, which is an example used in psychology to show whether children have the possibility to reason about higher order knowledge. And so some example used in cryptography, some example used in games, and so on. And that's it. So that's the tool in which you have here many examples that you can look into. Yes. So for instance, the Sally and Anne example works like this. So if you click here, initially you have Sally and Anne that are at home, okay, and Agent Blue has the marble in her hand, and Agent Red is at home. Then Agent Blue decided to put the marble into the basket. So when you click here, it performs the oh. Oh, no, it's okay. Yes, sorry, I will start again. Wait. Yes, so Agent Blue puts the marble into the basket, okay? And then she goes out like this. And then meanwhile, so here, when she puts the marble into the basket, actually all the agents are aware of this action. That's why there is only one possible world here. And now Agent A transferred the marble from the basket to the box, but Agent B here is outside, so he's not aware that the transfer has been made like this. And now when Agent B goes again inside, actually the puzzle is to ask where Agent B thinks that the marble is. And when you look in the possible world here, the sole possible world, you see that Agent Blue here thinks that the marble is still in the basket. So here we don't have knowledge, we have belief, right? And yes. So when you click here, it executes actions and it transforms the epistemic state, right? And this we will talk about that very soon. So this example has been used by roboticians and also by people in AI to build systems that are able to reason about false belief, like this one. So if you are interested, you can look at this different paper. Okay, so, and also, so this system, Hintica's world, is open source, and you can have a look to the source code, and it's completely a web app. It's written in TypeScript, so it's easy to add examples. So I want to also that like users can add examples like on the fly. Now it's not yet the case, but it will be soon. And several contributors have contributed to this project. So if you are interested in either coding or proposing ideas or improvements, do not hesitate to tell me. Okay, so epistemic logic. So as we have seen, you have models, right? You have epistemic models. So an epistemic model is given of a non-empty set of words, an accessibility relation for each agent, and a valuation function. So that's the epistemic states is this graph here. So you have here 4 possible worlds. You have an epistemic relation for each agent. So here they are in color, right? The epistemic relation for agent red is in red, and for the agent blue, it's in blue. And you have evaluation for each possible world. You say which atomic propositions are true or false. The syntax is as follows. So it's the standard modal logic. You have propositions, negation, the conjunction, the disjunction, and the knowledge operator. So this is written agent A. You don't see my screen, right? Do you see my screen?
Yes.
Okay, because
only the slide.
Sorry?
We can only see the slide.
So it's something changed, or
no.
You don't see the tool when I presented the tool?
Not on this slide. No.
Okay.
We only see the slide with the title syntax of.
Yeah, okay, that's perfect. Okay. No, because Zoom just sent me a message. Participants cannot see your screen. Okay, never mind. Okay, and so this is the epistemic operator. It's read as agent A knows that, or knows or believes that phi is true. Okay, so conjunction can be written with the Morgan rule like this. You have another modal operator, noted like this, k hat A phi, and it's read that agent A considers phi as possible. And it's the same considering something as possible as it's not the case that the agent knows that not phi. So he's imagining a possibility that phi is true. And the semantics is as follows. So P is true when P belongs to the set of true propositions in W. The negation is the negation, the OR is the OR. And knowledge is the property phi holds in all possible worlds. So in all possible worlds that are linked by the relation for agent A to the current pointed world, and in all possible worlds U, phi holds. So here you have a graphical representation of this. So for instance, agent A knows that B is muddy because in all possible worlds for agent A, which is the red agent, the property B is muddy holds. And here, agent A imagines himself as muddy because there is he imagines one possible world in which he is muddy, and this world is here. So in the tool, so you see the tool, right? Now.
Yes, that's okay.
Okay. So here you can write a formula. Does agent A knows that he is himself muddy? And you can here check, and the tool say, no, this is not true. But agent A will know that B is muddy. And you click here, and it says, yes, indeed, agent A knows that B is muddy. So when you are looking at examples, you can execute actions, and you can evaluate formula like this. So the practical session you can do at home. This is the syntax that is used in the Hintikaz world. So it's like a Lisp or a scheme syntax for proposition, negation, or and the knowledge operator and the dual of the knowledge operator, agent A considers phi as possible. And you can write any formula, and you can check whether a given formula is true in a given situation. We will not talk so much about common knowledge, but there is also, we can also introduce common knowledge, which is actually the fact that an agent knows that the other agent knows, that I knows, that you know, that I know, that you know infinitely often. So as many as you want, that a given property is true. So for that, you need to add a new operator in the syntax. So it means that there is common knowledge of phi among the group J. So if you take any sequence of agents so A1, A2, A3 till AN in group J, you will have that A1 knows, that A2 knows, that A3 knows, probability AN knows that phi is true. So here you have the semantics, and actually you take the reflexive transitive closure of taking all the edges from the relation of each agents that are in the group. Okay, so now two problems that we can consider. The first one is model checking. So model checking is you take as an input an epistemic state, and you want to check whether a formula is true. So this problem is actually the problem that is implemented in Hintika's world. So you have a situation that corresponds to a crypto structure, and you want to check whether a given formula is true or not. So this problem is easy to be solved. It's P complete. So this is rather standard. So I pass. And the problem is that usually models are very huge. For instance, if I take the examples of Minesweeper, you can have really the number of possible worlds is very huge and can even not be stored in a computer. So we use symbolic approaches to do model checking on this type of models. So even worse if you augment the size of the. And so we have implemented and studied succinct representations for this type of models. So this is a standard also in the verification community. So you can use either binary decision diagrams or use SAT to do model checking procedures for that. And in Hintika's world, the approach, the model checking of SAT is implemented, but unfortunately today I cannot show you because there is a problem with the server, because the SAT procedure is run in a server. So I'm sorry for that. So the another approach is to use theorem proving. So you can actually not look in one specific model, but look in all a class in a whole class of models. So you can check whether a formula is satisfiable, meaning that there exists an epistemic state that satisfies this formula, or to check that a formula is valid, or we also say that this formula is a theorem, if it holds in every possible states. Right. And so these two properties are valid, are dual. If phi is a theorem, it's the same of saying that not phi is not satisfiable. And especially, yes, that's all. So I will go quickly on that, but you can also axiomatize the set of validities. So if you have, for instance, a theorem like this, you can build a proof, so a sequence of formula that either are a tautology of Boolean logic, either is an instance of axiom K, which is this axiom. So if an agent knows that phi implies psi, then if agent A knows phi, he will know psi, and or obtained by the modus ponens rule. So if you already have proven phi and proven phi implies psi, you infer psi, or and can be obtained by the necessitation rule. If you have proven phi, you will also have proven that agent A knows phi. So axiomatization is interesting, and especially there is a paper that I like, because they use axiomatization to put a limit of the capacity of an agent to do reasoning by limiting the number of application of rules that you can perform. Because usually that's a drawback of epistemic logic. Epistemic logic, all agents are omniscience. So there is omniscience because they can they actually, an agent knows every theorem. Okay, and there is also link with the so-called justification logic and so on that I will not go into that. Okay. So we have already talked a bit about beliefs and versus knowledge. And actually, when you go here, you see that the relation is an equivalence relation, because we say that two possible worlds are actually undistinguishable for a given agent, and this corresponds to the fact that it represents knowledge. But when we were in the example of Sally and Anne, like this, here it does not correspond to knowledge. This is beliefs, and actually it's false belief. And here, when you see in the model, it corresponds. It's not an equivalence relation. You have an edge from this world to this world, but not on the contrary. It's not symmetric. So in the literature, there are some constraints on the model that corresponds to either knowledge. So knowledge corresponds to the fact that it's an equivalence relation. And for beliefs, it corresponds to the fact that it's KD for 5. So meaning that we have K, the action K that I already presented before. We have seriality. So each possible word has at least one epistemic successor. It's transitive and it's Euclidean. So this is depicted by the little pictures that you have here, and it corresponds to some axioms in the syntax. So A thinks that top is possible. If A knows phi, then he knows, well, if A believes phi, he will believe that he believes phi. And if not believing phi, he believes that he's not believing phi. So these are the positive introspection and negative introspection. Okay, so KD for 5 corresponds to beliefs, and having an equivalence relation. So this is called S5, corresponds to the knowledge case. Okay, so that's it. So here it's summed up here. You have here KD for 5 for beliefs and S5. So you take also T instead of D, and you will have an equivalence relation for the in the models, and it corresponds to knowledge. Okay, and last but not least, you have the complexity of theorem proving. So to know whether a formula is valid, and you have here the different theoretical complexity for the different cases. So whether you have either you have one single agent, and in this case, so the really important case are KD for 5 and S5, because it could correspond to beliefs and knowledge, while K you don't have introspection, for instance. So it's co-NP complete for a single agent, and it becomes p-space complete if you have several agents, and X-time complete if you furthermore you add common knowledge in the language. So this is a claim by Halpern and Vardy that model checking is more practical than theorem proving. The complexity are lower, but so it's P complete on the model checking if the model is explicit, but if the model is symbolic, it becomes p-space complete. Well, you can complain, because if satisfiability means that you are fully dealing with the syntax. You only have a formula and you want to know whether this formula is valid or not. While model checking, you deal with a model and you deal with a formula. But when you have symbolic model checking, you can also say, well, we have a language to describe the model. So it's also kind of everything is syntactic, but just one part of the syntax is used to describe the model and not to describe a statement. Okay, so now it's time to go into dynamic epistemic logic. That is to add action in the picture. 2 seconds. Duke, are you still here?
Yes, it's okay.
Okay.
We are you.
Okay. So now we'll talk about dynamic epistemic logic, which extends epistemic logic with actions. So first we will start with a discussion about how we model actions. So usually in the verification and model checking community, and also what used in what we'll present Aurélie Beynier, so in MDP, POMDP, decentralized POMDPs, and so on. Usually you describe actions by transition in transitions between state. You have this state, and you go from this one to this one by executing action B. So in the verification community, usually they have a program written, let's say, in C, and they transform that program or the execution of that program into a transition system. So maybe they use abstractions for replacing, for instance, an integer by an abstraction. Let's say the integer is either even or odd. So this makes that the transition becomes usually finite, and then they can do model checking on it. And when they are dealing with epistemic features, they will add epistemic relations on it. So the exact relations that we have discussed until now. Oh, there is a bug. What is going on here? Yes, so you will add edges like this. So for instance, this state and this state, agent red cannot distinguish these two states. Agent blue cannot distinguish these two states, right? And then they do either memoryless or perfect recall semantics to evaluate formulas on traces on this transition system. On the contrary, in philosophy and AI, it was also a trend to say, look, the mechanism inside an action is very important. And the problem is that if you take this approach here, you don't see the mechanism of the action itself. So for instance, you cannot say that an action is public or private, right? Public means I can announce to all of you that I have a given card, okay? And you will all know that I have that card, and you will actually there will be common knowledge that among you that I hold this specific card, right? On the contrary, I can do a private announcements. For instance, I can say only to Aurélie that I have this card, and you will not be aware that I have told Aurélie that I have this card, or maybe you will be aware that I have sent a message to Aurélie about a given card, but you will not know which one. Okay. Also, an action can be public. I can do something publicly. I can also do something privately. For instance, removing a card from a deck secretly. Another mechanism that have been studied is the mechanism of belief revision. So you can learn a piece of information, although you believe the contrary. So you have also a whole literature about belief revision. So the notion of mechanism is important when you design how you will how an action will change the knowledge of the different agents. So the solution is that comes into the picture is really dynamic epistemic logic, because in dynamic epistemic logic you will be able to figure out what is the type of a given action. So first I will explain to you how we model an action in dynamic epistemic logic. Actually, dynamic epistemic logic generalize the notion used in classical planning. So in classical planning, you have states, for instance, evaluation. You for each atomic proposition, you say whether it's true or false. So here, the agent has this card, right? And an action is described by a precondition, so a formula that should be true when you perform that action, and a post-condition, which explains how the world is changed. So here, the agent will not have this card in his or her hand anymore, because this variable becomes false. Now, how we generalize that for dealing with knowledge, we kind of requickify the models of classical planning. So how we model state, we already have explained that. So you have a graph with epistemic edges like this, and you have a given pointed world that denotes the actual world. And now, how do we model actions? Actually, we do exactly the same. So you take the actions from classical planning, and these actions will become the nodes of a graph, and you can link this different world with epistemic relation. So for instance, here, the real actions that is occurring requires that the agent has discard, and we have the effect that this discard will not be in the hand anymore, while for agent blue, the sole action that is actually currently being executed is for him that, so it's a false belief, of course. For him, nothing happened. So meaning that the precondition is true, right? And the postcondition is trivial, meaning that nothing is the values of the atomic propositions the values are not changed, and that's it. And now you can see how we compute the next state, so the next epistemic state, right? That corresponds to the new situation, having from this situation executing this action. So how do we compute the next state? We do the so-called product update. The product update is computed as follows. So you compute a product, meaning that for each world and each atomic action in the action model, this is the action model. So for each one, this one, this one, this one, this one, and for this one, well, all the pairs, you will have potentially a new world here. So you take this this world, right? And you check whether the precondition is true or not. Actually, the precondition is true. Therefore, you will have a world here. And this world is obtained, by applying the postcondition. So here you say that the agent does not have discard. So you have here the negation of that proposition. Now here you have the agent does not have that card, right? So the precondition here is false. Therefore, you will not have a world here. Here the precondition is true. So true is true in all worlds, right? So you will simply copy here the two worlds. And now for the edges, you will have an edge when there is an edge here and an edge here. So there are self loops here. Each time you have self loops. So for instance, here you have a blue edge from this world to this one, because there is an edge from here to here, and an edge from here to itself, because there is an edge loop. And that's it. So formally, no, we will see afterwards the definition. Yes. Yes. So you have also in the literature plenty of papers dealing with kind of specific actions or a specific knowledge. For instance, here in this paper, for instance, you have specific atomic propositions saying that a given agent will pay attention to what is done in the world. And actually the evolution of knowledge is computed in the same way that we have seen, but you don't have the action models in the language because they are a bit tedious to build. Actually, they are built on the fly. So the idea, the big picture is you have a syntactic specification. So you can have an agent, like I have said, an agent is paying attention, or an agent is seeing another agent, and so on. And from it, you compute the models of dynamic epistemic logic. So you compute the epistemic state and you compute the action models. And then if you want, you can also unravel all the temporal structure, and you will obtain an epistemic temporal model, as we have discussed really at the beginning when we have seen what is going on in the verification and model checking community. And so the advantage of having a syntactic specification is that it's easy to specify, it's succinct, but the problem is that you have ad hoc languages, and you have to say like A sees B, or A pay attention to what is going on, and so on. So it's handcrafted. The model of dynamic epistemic logic, so as we have seen, it's really elegant. It's a simplification of classical planning. It's succinct. Succinct in the sense that we will see that actually the model that you will have if you unravel the structure can be infinite, whereas here is described by a finite set of action models. So in this sense, it's succinct. You can also have a classification in terms of action types. It has a probabilistic extension, belief extension with belief revisions, and so on. But the semantics itself is built in. It's perfect recall and synchronous. So if you want to tune that, you have some work about that, but it's usually it's not done like this. And here it allows for any kind of semantics, but the type of action is completely lost. Here you don't see exactly the type of actions, and it's not succinct. It can be the unraveling can be infinite. So as I have seen, dynamic epistemic logic has a connection with multiple other domains. So for instance, in AI, it has connection with belief revision planning. In verification, it has connection with epistemic temporal logic, strategic reasoning, and so on. Okay, so now we will define formally what we have seen. The action models are also so-called event models. So it depends on the paper that you are reading. The two terminology are used. A public announcement, actually, to see that an action is a public announcement, it's because the type of graph is like this. You have a single node, right, where the precondition is the formula that you announce, and the postcondition is simply nothing is modified. It's the trivial postcondition. So as you see here, with action models of dynamic epistemic logic, you really see the type of the action. Here you see that this action is a public announcement because you have a precondition, you don't have a postcondition, and you have a single node in the action model. Private announcement, usually the form is like this. You have a precondition, which is the announcement that is performed, right? You have here the agent or the agents, an edge for the agent that is listening, or the different agents that are listening to that particular announcement. And for the others here, so for B that is not listening, nothing special happened. So it means that the precondition is true, and also the world is not modified. If we want to model the fact that while agent blue is outside the house, the fact that the marble is transferred from the basket to the box, you will model like this. So for agent A, actually the marble should be in the basket. Now it's not in the basket, and it's settled in the box, right? While for agent B, nothing happened. So it corresponds to this particular action model. So the formal definition of an event model is you have, so it's really the same definition than for a cryptostructure for denoting an epistemic state, but we just replace the state by events. So you have a collection of events for the nodes. You have accessibility relation for each agent, and for each event you have a precondition, right, which is an epistemic formula, and you have a post condition, which is a collection of assignments. So assignments means that for all atomic propositions, you will assign an epistemic formula that will be evaluated in a given world, and whether it's true or false, you will have the Boolean assignments, you will perform the Boolean assignments to that particular atomic proposition. And in the same way, action models are usually pointed, and we say that you have a pointed action model where we denote a particular event, E, which is the current event model. So usually the model is is sequential. One event model are executed one after others. And there is a version of also with concurrent event model, meaning that each agent will perform its own event model and they will be executed in parallel, concurrently. So there is a generalization of this definition to concurrent models. Okay. And also, yes, if you want to model deterministic action, so it's single pointed, this is the current action that is executed and that's it. If you want to model non-deterministic actions, you will have multi-pointed event models, meaning that maybe it's this event that is executed or maybe it's this one. So this corresponds to non-deterministically choose a value for P, either true or false. A will actually be aware of the value that is chosen. Actually, it's a private announcement to A, while B is not knowing the value that of P. Actually, for him, the value has not been changed. Okay, so this I have already said with a different example. So an action is said to be public if you have a single point like this and self loops. It's said to be non-ontic when all the post conditions inside are trivial, meaning that nothing change, right? So for all atomic proposition, post EP is still the value of P, and that's it. And this is just the effect now of an action we already have seen, but we will define a bit more formally. The effects of a public announcement. So if you have only a single point in the event model, the precondition is phi and postcondition nothing change. Here it corresponds to take all the worlds in which phi holds, right? And phi must hold also in the current world. And if you announce phi, it means that you just delete the world in which phi does not hold. So you can check in Hintika's world, for instance, here, if you publicly say that A is muddy, you will delete all the worlds in which A is not muddy. So these worlds will be deleted. So if you click here, boom, now you made the announcement that A is muddy. So only worlds in which A is muddy remain. And for an updated product, so we already have seen an example, so I will not show this example. It's already enough. So the update product formally, it's defined as follows: the set of worlds is the pairs in which the precondition holds, right? The relation, it's kind of I should not say that, but it's kind of synchronous. It's not synchronous because it's not about time, but it's synchronous because you require for all the coordinates to be related. So the successors of WE are the pairs W prime, E prime, in which W prime is a successor of W and E prime is a successor of E in the respectively in the epistemic state and in the event model, and the valuation is the one computed after by applying the post condition. Okay, so this we will not need. Okay. So I will go quickly in the part of verification of plans, and then I will talk about epistemic planning. Or maybe I will talk directly about epistemic planning because we are a bit running out of time. And I want to show you what is the nice picture of epistemic planning when we model actions with even models. So first, it has been shown that epistemic planning in its full generality is undecidable. So the problem is stated as follows. You have an initial state represented by epistemic model. You have a repertoire of actions, which is finite and represented by action models or even models, that's the same, and a goal, which is an epistemic formula, and you want to know whether you can reach a final state that satisfies the goals from the initial state by executing actions from the repertoire. And the big picture is as follows. So usually it's undecidable. And actually we have classified the decidability with respect to the fact that there is postcondition or not. So by saying no postconditions, I mean the postconditions are trivial. You don't change the world. And having Boolean postconditions. And we also classify with respect to the modal depth of the precondition. So for instance, the modal depth is the number of nested epistemic operators that you are allowed to put in your preconditions. So for instance, A knows that B knows that A knows that B is of modal depth 3, right? And here are the different papers in which the different results are shown, but there is also a survey that sums up all the different results. So it's undecidable. As soon as you have modal depth 1 for the precondition and Boolean postconditions, it's undecidable. So it's undecidable all here. If you have no postcondition but modal depth 2, it's undecidable. We know that it's decidable when you have modal depth of preconditions 0, so meaning that you have Boolean formula in the preconditions. And here you have an open problem. So actually we don't know whether epistemic planning is decidable if you have no postconditions and the modal depth of preconditions is 1. And I think it's a challenging open problem. Okay, actually it was proven that epistemic planning is already undecidable if you have, so in the original paper it was proven that it's for 2 agents, Boolean postcondition, modal depth smaller than 1, but actually it's also undecidable if you have a fixed repertoire, only 1 action, and you only have 6 atomic propositions. This is sufficient for having epistemic planning undecidable. So if you are interested in, you can look in Hintika's world. The proof is shown, because what we are doing is that we are simulating the execution of a cellular automaton, and the reachability of this type of machines that are Turing complete is undecidable. So I don't know if you know cellular automaton. It's like you have a bunch of cells, and each time you apply a given rule. So you have a set of rules here, which says if you have a cell which is dead, alive, this cell will become alive. And each sequence of 3 cells, you will apply to the middle cell, you will apply a given rule like this. And actually we encode the configuration the configuration of a cellular automaton into an epistemic state, and the encoding is really simple. The real world here is like this, and you will have the state of the cell here, which is of the middle cell, which is 1. And when you go in the possible world of the blue agent, right, and when you look at the actually you have two variables. You will have one variable that will give the state of the cell, and one variable which say whether the agents are flipped or not. And when you go in the other world, where the agents have flipped, you will see the value of the cell which is on the right. And when you go like this, you will have the other values, and in the other direction, you will have the values when you go on the left. And we have designed actually we have designed an action model which exactly simulates the execution of the automaton. So here you have the example. Here, if you want to study that, you have the initial state, which represents a given successor, a given sequence of cells, and you can, by clicking here, you will compute the next epistemic state that will correspond to the next state of the cells of the cellular automaton. And then we pinpoint. So for that, you have to look into the paper. We have a special, very small cellular automaton that is Turing complete, and for that we get the result about the 6 atomic propositions. So it means that if you unravel the structure, the epistemic temporal structure, so here you have the epistemic model, and when you perform actions like this, you will get a sort of tree with epistemic transitions. And epistemic planning can be seen and rewritten as a first order query in this big picture, in this big structure, first order structure. So usually this structure is Turing complete because epistemic planning is undecidable, and actually can embed the execution of a cellular automaton. But interestingly, it was shown that when the precondition and postcondition are Boolean, it becomes decidable. And so this was originally proved by you and Al in this paper. But in this other paper, there is a very elegant proof where they showed that this first order query actually is made on a structure which is very regular, because the preconditions are Boolean, and this type of structure are called automatic structures. And therefore, in this type of structures, the model checking of first order logic is decidable, and hence the epistemic planning is also decidable on this type of structure. And this result can be also extended to, well, epistemic linear mu calculus, but we will not go into details like this. So automatic structures are very nice. There are structures that are defined by automata. So for instance, this very neat structure, the integers predicate is even and smaller than. All this set, then these two predicates can be defined by automata. So we will not enter into details because you can see the slides and we are a bit lacking of time. But there is a strong connection between epistemic planning and automata theory in here. And also epistemic planning has been generalized to multiplayer games. So I am running a bit of time, but the idea is a bit the same. Instead of computing a plan, you will compute a strategy. And some results have been shown there. So you can look into these papers. You have plenty of results. So it's undecidable in general, sorry, even when the precondition and postcondition are Boolean. And this corresponds to the seminal paper of Reif and Peterson. And then you have other results here of decidability and so on. So here you have the big picture of the complexity of epistemic planning. I have talked about the undecidability and also about this decidability here. And you have, if you restrict the type of actions, you will have smaller complexity in the for epistemic planning, either if you have one centralized planner, so the standard epistemic planning, or if you have many agents like this. And the seminal paper of Reif and Peterson lies here and corresponds of having precondition Boolean and precondition and postcondition that are Boolean. Okay, so I think I will stop now. And so you have an overview of well, how we can define action in dynamic epistemic logic, where the type of action is actually very visible. It's given by the structure of the graph of even models or action models. And you have seen that you have results in epistemic planning depending on the type of actions that are allowed in plans. So that's somehow the idea of epistemic planning until nowadays. So thank you for your attention.
Okay, so as mentioned by Francois, the agent may not have perfect information about the action or the knowledge of the other agents. So we will try to consider several research issue in planning. Like multi-agent planning, where several agents interact in the same environment. We also consider non-deterministic action, when the outcome of the action are uncertain. And we also consider that action may last over time or have temporal constraints. So temporal planning will be described by Frédéric in the third part. And in my second part, I will more specifically focus on multi-agent planning, where the agents have partial observability of the system and must reason from their observation about their plan and coordinate their plan. So to describe the big picture of this part, we consider deliberative agents acting in the same environment. So the agents are deliberative. That means that the agent may build a representation of their knowledge about the state of the system and the other agent. And the agent will reason about from this knowledge to make a decision. We will consider cooperative agents. So cooperative agents share a common objective. Usually it is a measure of performance to maximize, but it may also be described by a goal, a common goal that the agent want to reach. So these cooperative agents are taking a sequence of decisions from partial observation about the system, and they have to coordinate their action to maximize the performance. We want each agent to make her own decisions, so we consider distributed decision making, where each action takes autonomous decisions based on her partial knowledge about the state of the systems. And as the agents act in the same environment and share common goals or common measure of performance, the performance of the agents rely on their interaction. So we need to consider coordination between the agents. So we want the agents to elaborate, to plan cooperative strategies based on partial individual knowledge about the system. And we also want the agent to take into account uncertainty about the action outcomes. So this type of problems can be encountered in many real-world applications. For instance, if you consider a fleet of mobile robots that have to explore an unknown environment. So the common objective of the robots is to explore all the parts of the environment. And the robots have limited observability about the system because of its limited sensor and because of the topology of the environment. For instance, a robot cannot sense behind a wall. And the action of the robot, the outcome, the action outcomes of the robot are uncertain because the environment is unknown. The robots are not able to anticipate all the consequences of their action. To mention other possible application, on the right upper part of the slide, you can see a sensor network where each sensor is an agent. So each agent has limited sensing capacities of the environment, and we want all the sensors to coordinate in order to detect, for instance, seismic activities or volcano eruption. So sensor must coordinate their sensing action of the world to make accurate description of the world. On the lower part, you can see a set of satellites which have to make observations of the Earth. And in this problem, satellites have to cooperate to allocate observation tasks in order to perform as many tasks as possible. And in this example, you have very restrictive constraints on the action. For instance, you have temporal constraints. You have to make an observation of the France, for instance, when the satellite is at the right place, and you want the observation to be done between midnight and 3 a.m. So you have temporal constraints on the action. And of course, you have to respect the orbit of the satellite around the Earth. And on the right lower part of the slide, you have an example of an application when, in fact, you have a virtual environment that you want to animate with virtual characters and virtual vehicles. In this case, it is a 3D representation of Paris. And we wanted to animate the Paris with virtual pedestrian and virtual cars and bus and so on. So in this case, you have a very large problem of coordination and a highly dynamic system, because or you have to coordinate pedestrians and vehicles and so on, and you cannot predict the plan of all the agents in the environment. So why do we have to consider partial observability and uncertainty? So first, partial observability of the system comes from the limited sensing capacities of the agents. If you take, for instance, robots, robots have limited capacities with their sensors, and they cannot perceive all the environment. and because of limited capacities, but because also of the environment topology. As I mentioned before, a robot cannot see behind a wall or cannot see the agents that are 10 kilometers from her. The partial observability also come from non-observable information. That is, there is some information that cannot be sensed by the other by an agent. For instance, if you think about the internal state of another agent, that cannot be sensed by a camera or a sonar equipped on a robot. So from her sensor, a robot or an agent will obtain partial information about the state of the system, and it will have to make a decision based on this individual partial observation. It has to be mentioned that individual observation can be noisy. For instance, an agent can sense a false wall, that is a wall that does not exist, or maybe can sense a false pedestrian or false obstacle in the environment. So this noise on the observation has also to be considered when making decision. So it has to be considered that some observation may not describe exactly the environment. So one solution to cope with this partial individual observability is to allow the agent to communicate and to share their individual observation. So in this case, we say that we refer to joint partial observability. So the joint observability is the observability that is obtained by the agents when they share all their individual observation. But in some case, even if the agents are able to share all their observation, they may not have enough information to deduce the state of the system, because some information about the state of the system is not observable by any agent. So in this case, we say that the state is jointly partially observable. And when the agents can deduce the state of the system when they share all their observation, we say that the state is jointly fully observable. So this is we will see that it makes a difference when we plan the action of the set of agents. So that is for partial observability. And about uncertainty. So in fact, the uncertainty about the dynamics of the system may have two sources. First, we can talk about the state of uncertainty. So the state uncertainty arises from the partial of the observability of the state of the system. So because there are some information about the state of the system that we cannot observe, we are uncertain about the real state of the system. So this is state uncertainty. And uncertainty also deals with the model uncertainty. And model uncertainty arises from the imperfect modeling of the environment's dynamic, or the imperfect actuators of the agent. So in fact, if you consider that you are in a very highly dynamic environment, usually you are not able to model all the effects of all the components of the system dynamics. So your model of the system dynamics is imperfect. So you have uncertainty on the effect of the action. It usually arises in a robotic application where you are unable to predict all the environment components that will impact the outcome of your robot action. So we have uncertainty arising from partial observability of the system and also from imperfect modeling of the environment dynamic. And we want to take into account this uncertainty when making a decision. So there are different models to represent uncertainty. And so I refer to the book of Alpern if you want more details about the representation of uncertainty. And in this talk, we will focus on probabilistic functions, where in fact we will represent the uncertainty by a transition function, T, where it gives the probability to move from state S to state S prime when an agent executes an action A. Of course, if you sum over all possible outcome state S prime for a given state, state S and a given action A, all the transition probability will sum to 1. So we consider probabilistic functions to represent the uncertainty about action outcome. So to make a picture of what happens in the system. So in this case, we consider that we have two agents, two robots. So the agent will have to make individual autonomous decisions from their observation about the system. So in this case, you see that agent 2 decides to execute agent A2, and agent 1 decides to execute action A1. So A1 and A2 make the environment moves from state S to state S prime. So this this transition can be represented by our transition function. So the uncertainty about the transition is represented by a probabilistic function. And once the agent has moved to S prime, they obtain a reward R. So this reward is common to the agent as we consider cooperative agents. And this is the sum of the rewards that the agent may want to maximize, for instance. So when the system moves to S prime, the agents do not observe S prime. In fact, they observe partial information about the system. And in our case, agent 1 obtains the observation O1, and agent 2 gets observation O2. And then agent 1 will have to make a decision from this observation O1, and agent 2 will have to make a decision based on her observation of the system, that is O2. Then the agent take new decisions. They execute a new individual action in the system, which makes the system move to a new state. They obtain a new reward, and so on, until a given number of decision step, which is called the horizon of the decision problem, and usually denoted as H. So if we consider a benchmark problem, here that is a multi-agent tiger decision problem. So this is a problem which is used in benchmark in multi-agent planning to test models and algorithms. So here I present the problem to exemplify the decision problem. So in the multi-agent tiger domain, we have two agents which are in a corridor. And in this corridor, there are two doors. Behind one door, there is a tiger, and behind the other door, there is a treasure. And we want the agents to cooperatively open the door with the treasure. If the agents open the door with the treasure, they get a high reward, which is, for instance, the gold that is in the chest. But if the agent opens the door with the tiger, they get hurt and they obtain a penalty. So we want the agent to cooperatively open the right door. But the agents cannot communicate and cannot see behind the door. So they only have partial observation about the state of the system. And in fact, they can hear the tiger behind the left door or behind the right door. So at each decision step, each agent can choose to hear or to open the door on the right or to open the door on the left. And we want the agent to open simultaneously the door of the treasure. So this is a decentralized decision decision problem because each agent has to make autonomous decision based on partial information about the state of the system. So this partial information is a set of observation each agent can obtain when it's here behind the doors. And we want the agent to maximize their joint reward. So we want them to open as often as possible the right door. So another benchmark problem that is often used in the multi-agent planning community is the meeting on a grid problem. So in this problem, we have two agents which are moving on a 2x2 grid. So this is a very small environment. And in this problem, agents can not perceive their position on the grid. They only perceive a wall on the left. So you have a wall here and you have a wall here. So you can perceive a wall on the left or a wall on the right. And this observation can be noisy. So you can perceive a wall that doesn't on the left if that does not exist, and you can perceive a wall on the right that does not exist. So, for instance, the agent on the left upper cell should perceive a wall on the left. But if it obtains a noisy observation, it can perceive no wall on the left, a wall on the right, and maybe it can perceive no wall at all, or a wall on the left and a wall on the right. And so some observation does not match with the real description, the real world, the real environment. So in this problem, the objective of the agent is to stay as long as possible in the same cell. So, but they cannot communicate, and they do not perceive their own position and the position of the other agent. They only perceive the wall with noisy observation. So I will now move to the modeling of the problem. So in fact, we are facing a sequential decision problem with partial observation and uncertainty on the action outcome. So in a single agent decision problem, this decision problem are usually formalized by Markov decision processes. But in fact, a Markov decision process only represents a single agent decision problem. So to formalize a multi-agent decision problem, Boutillier has proposed an extension of the single Markov decision process to a multi-agent Markov decision process. So this is a direct extension of the single case. So in an MDP, if you know Markov decision problem, a single agent Markov decision problem, in a single agent Markov decision problem, you have a set of state, a set of action, a transition function, which formalize the uncertainty on action outcome, and you have a reward function, which formalize the agent objective. So in a multi-agent Markov decision process, in fact, you had alpha, which is the number of agents of the system. And you also have a state of states. So S is a state of states of the system. And the crucial difference is the definition of the action set. In fact, an action is not the action of a single agent, but in this case, the action is a joint action. In fact, it is a set of actions executed by each agent. So a joint action A is composed of the action of the first agent, the action of the second agent, the action of the third, and so on. So in fact, by representing the set of action of the agents, you can formalize the interaction between the individual actions of the agents. So in fact, the set of action is a set of joint actions, which are defined based on the set of individual actions of each agent. So the transition function is then defined on the set using the joint action. So the transition T gives the probability to move from S to S prime when the joint action A is executed. And by considering the joint action, you are able to represent the interaction between the individual actions of the agents. And the reward function is also defined using the joint action set. So in fact, an MMDP is like a single agent MDP, but you will have to consider a larger set of action because you are considering joint actions. So an MDP can be solved with standard algorithms for MDP. The output of such an algorithm, a solving algorithm, will be a joint policy, which in fact represent the set of individual policy of the agents. So in fact, you obtain a policy when you solve an MMDP with a value iteration of policy iteration, for instance, which are standard algorithms for MDPs. So you will obtain a policy which maps each possible state of the system to a joint action. And you can decompose this joint policy as a set of individual policies, one policy for each agent, which map for each possible state of the system to an individual action for the agent. So this is what is explained here. You obtain a joint policy pi, which can be decomposed as a set of individual policies P1 to pi n, where pi e is the individual policy of the agent I, and it is defined, it maps each possible state of the system to an individual action of the agent. But in fact, if you want the agent to apply this individual policy, the agent must know the state of the system, because the policy maps each state of the system to an individual action. So the agent has to observe the state of the system. That means that each agent must have full observability of the state of the system. And in fact, this assumption rarely holds in multi-agent systems. As I mentioned before, in fact, in many applications, the agents have partial observation about the state of the system. And even if the agents are able to communicate all the observations, they are not able to deduce the state of the system. So the agents do not have individual observation of the state of the system. So MDP can be used to plan for multi-agent decision problem, but in very specific settings where each agent can observe the state of the system. When the state of the system is not individually observable, in fact, we turn to this DEC-POMDP. So DEC-POMDP is for decentralized partially observable Markov decision processes. And in this case, we introduce, so we have a set of agents, we have a set of system states. Like in MMDP, we have joint actions, we have a joint transition function, but we also formalize the observation of the agents about the system. So we have a set of joint observations, which are defined from the set of individual observations of the agents. And so this represents the partial observability of each agent about the state of the system. And as observations can be noisy, we also define an observation function which represents the noise about the noise dealing with the observation. So the observation function omega is the probability of observing O when the agent executes joint action A from S. So for a given S and a given A, that means that the agent can obtain different observation, joint observation. And this is the probability to obtain a given joint observation O. So that encodes the noise on the observation. So like MMDP, we also have a reward function, which in fact encodes the objectives of the agents. And this is a joint reward as we are considering cooperative agents. So the reward is obtained by the set of the agents. And we do not consider how to distribute the reward among the agents. In fact, we want to maximize the joint reward obtained by the set of the agents. And when the initial state is not known, is not observable, we also define B0, which is the initial probability distribution over the state of the system at the first decision step, so at t equal 0. So this is for DEC POMDP. And if you remember the literature about MDP in the single agent case, you have MDP and you have POMDP for partial observability Markov decision problem. So we can question what is the relation between DEC POMDP and DEC MDP. So we, in fact, a DEC POMDP is a specific case of DEC POMDP. So in DEC MDP, you do not have partial observability, but in fact, it is not. It does not mean that you do not have partial observability at all. In fact, a DEC POMDP is a specific case of DEC POMDPs where the agents have collective fully observability. It means that if the agents share all the observations about the system, they can deduce the state of the system. But in fact, when the agents execute their strategies, when they execute their action in the environment, they still obtain individual observation about the state of the system. So a DEC MDP, in a DEC MDP, you cannot remove the state of observation and the observation function. You have to keep this information because your agents still have partial observability about the state of the system. But you have a specific property for a DEC MDP where that says that the system is collectively fully observable. So as I mentioned in the slide, it is important to note that each agent does not fully observe the state of the system in a DEC MDP, and each agent still obtains partial observation. So that means that the description of a DEC MDP is the same as a DEC POMDP. You have the same components, and you have to define an observation, a set of joint observations, and an observation function. So if we want to represent the relationship between these different type of Markovian model, so the DEC POMDP is a more general model. DEC MDP is a specific case of DEC POMDP where the agent has joint full observability. A POMDP is a specific case of DEC POMDP where you have only one agent, and MDP is a specific case of POMDP with full observability of the state of the system and one agent, and it is a specific case of DEC MDP with only one agent. So if we come back to the multi-agent tiger domain and we want to formalize the problem as a DEC POMDP, so we have to define all the components of the DEC POMDP. In this case, in the multi-agent tiger domain, the state of the system is in fact represented by the position of the tiger. The tiger is behind the right door or the left door. So you have two states. The tiger is behind the left door, SL, or the tiger is behind the right door, SR. In fact, you don't have to represent the position of the treasure, because if you have the position of the tiger, you can deduce the position of the treasure. The set of action has to be defined by the set of action for the first agent and the set of action for the second agent. In this case, we have two agents. So in fact, both agents have the same set of actions. Each agent can open the left door, open the right door, or you can listen. So a joint action will be a will combine an action for the first agent and an action for the second agent. So in this case, we have 3 individual actions for each agent. So we have 3 by 3 joint actions. So we have 9 possible joint actions. The first agent can open left and the second can open left, but you also have the first agent open left and the second open right, the first open left and the second listen, the first open right and the first open left, and so on. So you have 9 joint actions. Next, we have to define the partial observations of the agent. So each agent, both agents have the same set of observations. In fact, the agent obtain observations when they perform the action listen, and they can hear the tiger on the left, or they can hear the tiger on the right. So we have 2 independent observations, individual observation. The transition function is very specific in this problem, because in fact, when the agents listen, the state of the system does not change. The tiger remains at the same position. So in fact, the transition function is used when an agent opens a door. And when an agent opens the door, you discover where is the treasure and where is the tiger. And you have to start a new game. And you place the tiger behind the left or the right door randomly. So the transition function specifies how the probability that the tiger is moved on the left or is moved on the right when you start a new game. So the observation function is encode the noise on the observation, and in fact it encodes the fact that an agent hears the tiger on the left, whereas the tiger is on the right, and it hears the tiger on the right when the tiger is indeed on the right, and so on. So you can hear the tiger on the wrong, behind the wrong door. And this is encoded with the observation function. And finally, the reward function encodes the objective of the agent, as we want the agent to cooperatively open the door where there is a treasure. We give a high reward for when the agents both open the door of the treasure, and we give the penalty when the agents open the door of the tiger. So as we are running of time, I will skip the representation of the meeting on a grid problem as a DEC POMDP, and I will move to DEC POMDP solving. So once we have formalized a multi-agent sequential decision problem as a DEC POMDP, we then want to solve this decision problem. And optimally solving a DEC POMDP, in fact, consists in finding a joint policy pi, which is composed of a set of individual policies, one individual policy for each agent. So pi1 is the policy of the first agent, and pi n is the policy of the last agent. And each individual policy, in fact, maps each possible history of observations of the agent to an action. So it is important to understand that in an individual policy for an agent, in fact, to make a decision, the agent has to consider all the observation it has obtained from the beginning of the execution. So considering only the last observation is not sufficient to make an optimal decision. You have to make your decision by considering the the history of observation you made from the beginning. So at the first decision step, you have no observation, so you will have to make a decision based on an empty history. But then, for instance, in our case here, the agent take action A1, and then it can obtain observation O1 or observation O2. So at the second step of at the second decision step, the agent has obtained one observation, O1 or O2, and it has to make a decision based on this observation. Then, so for instance, in our case, if the agent obtains observation O1, it then make decision A1. And then the agent will have to make a new decision. It has obtained, and this new decision at the third decision step must consider the first observation made by the agent and the second observation made by the agent. So in our case, you can see that if the agent has made observation O1 and then O1, it takes action A2. But if it had made observation O1 and then O2, it takes action A3. So for each possible history of observation, the agent make a decision. So in fact, when you solve DEC POMDP, you obtain such a decision tree for each agent. So this decision tree represents the individual policy of one agent, and a joint policy is a set of such decision trees. However, optimally solving a finite horizon DEC POMDP has been proved to be next complete. So it is a very hard problem to find a set of optimal individual policies. So we can intuitively see why. So if we consider the multi-agent tiger decision problems that we described earlier, and you assume that you have to make 3 decisions. So this decision tree represents the optimal individual policy of the first agent in the DEC tiger problem when you are planning for 3 decision steps. So at the first step, the agent will listen. If it hears the tiger on the left, it will then listen again. And if it hears the tiger on the left once again, it will open the door on the right. But you can see that if the agent listen, hear the tiger on the left, then listen, hear the tiger on the right, so it hears the tiger one time on the left and one time on the right. So it has a high uncertainty about the position of the tiger. So it keeps listening at the third decision step. And you have the symmetric with the right, the other observation. Then, if you plan for 4 decision steps, you see that you have one more decision step in the decision tree. And in this case, you can see that the agent starts listening. Then if he hears the tiger on the left, he listens again. And if it hears the tiger on the left, it listens again. And if it hears the tiger on the left, it opens on the right. But if you have mixed observation, you hear on the left and you hear on the right. So in this case, for example, here on the left, here on the right, here on the left, the agent keeps listening because he is too uncertain about the position of the tiger. So the problem is to, when solving a DEC POMDP, the problem is to compute such individual strategies that will maximize the expected reward of the agents. And as mentioned before, this is the next complete problem. So in fact, most of the algorithms that are solving DEC POMDPs are centralized algorithms. So in fact, in DEC and POMDPs, DEC is for the execution. The execution of the policies are distributed, but the planning can be centralized. So as represented by this figure, you can see that during the offline phase, so when solving the problem, you can use a centralized centralized entity, which computes the policies, the individual policies of the agents. Then you send the policies of the agents to each, you send to each agent her policy, and the agent will use this individual policy to execute her action during the online phase, during the execution. So in fact, most of the existing algorithms for solving DEC POMDPs are centralized, and you can exploit the fact that the planning is centralized to make the problem easier to solve. But in fact, it remains, even if the planning is made offline in the centralized way, even in this case, the planning remains very difficult. So to sum up, a naive approach is to use brute force search to enumerate all joint policy, to evaluate each possible joint policy, and to select the policies that maximize the performance. But in fact, the number of individual policies to consider grows exponentially, and it is not possible to use brute force search to solve DEC POMDP. In this case, you can see I consider two agents with two actions and two observations. So if I am planning for one decision step, I have two individual policies for each agent. So I have 4 joint policies. If I am planning for 2 decision steps, I have 8 individual policies for the first agent and 8 individual policies for the second agent. So I have 64 joint policies, and so on when I increase the number of decision steps, so the planning horizon. So in this table, I sum up the number of joint policy to consider if we use brute force search. So the first column gives the number of decision step. The second gives the number of individual policies for each agent. And the third is the number of joint policies to evaluate if we use brute force search. And you see that for Horizon 4, it becomes impossible to enumerate all joint policies. Use tricks to make the search of the optimal policies more efficient. And you can use bottom-up approach like dynamic programming. You can use top-down heuristics like the one used in multi-agent both to make the solving more efficient. So I will not detail all the approach, but you can also use iterated pruning of dominated strategies, like what is done in game theory. And in fact, I will not describe all this approach. So I just have a slide that sum up most of that sum up a large set of existing approach. So you have optimal approaches which use iterated pruning of dominated strategies. You can use heuristic to guide the search, like A-star heuristics. You can also, and that is the most efficient approach known today. So this is which consists in fact, translate the problem into a single MDP. That is, in fact, you use the fact that the problem is solved in a centralized way, and you translate your DEC-POMDP into a single MDP, which is defined on occupancy states, and you solve the single MDP with a single agent algorithm, and then you can translate to joint policies. So this is the most efficient approach to solve optimally DEC-POMDPs. And you also have approximate approaches, so where you can find Nash equilibrium or approximate policy without guarantee on the type of strategies. The main problem of approximate approaches are that it's very difficult to estimate the error on the policy and the distance to the optimal policy. And some approaches try to combine to use reinforcement learning or Monte Carlo expectation maximization to solve the problem. So I will finish with a comment about the strategies that are obtained by DEC-POMDPs. In fact, as you have seen, a strategy which maps each possible set, each possible history of observation to an action. And the main problem of these strategies are one of the problem is that they are far from being explainable or interpretable. And in fact, and there are many joint policies to consider. In fact, one perspective would be to compute more interpretable strategies and more compact strategies. And one tentative to define such strategies is based on qualitative decentralized observable Markov decision problem. So in qualitative DEC-POMDP, the transition function does not give the probability to move to each possible state, each possible outcome state S prime, but in fact, it gives the set of possible outcome state S prime without probabilities. And when we consider qualitative decentralized partially observable Markov decision problem, in fact, we want to compute a joint policy that guarantees that a goal state will be reached by the agent. So the complexity is the same of qualitative DECPOM-DP is the same as the one of standard DECPOM-DPs, but in qualitative DECPOM-DP, it has been proved that the joint policy of the agent can be represented as a knowledge-based program. And in fact, in a knowledge-based program, you define the policy with a compact representation of the problem as the one presented by Francois about epistemic logic. So you can refer to knowledge-based program and qualitative DECPOM-DPs for more details. But in fact, qualitative DECPOM-DPs is the first perspective to obtain more compact representation of the policies. The main issue that remains is that we know that we can represent more compactly the policies of qualitative DECPOM-DPs, but we do not know how to compute these policies. So the research issue that remains dealing with DECPOM-DPs is to define approximate algorithms that gives a quality guarantee about the solution that is obtained. Scalability still remains a challenging problem for DECPOM-DPs, and as I mentioned, policies that are computed are far from being interpretable, and one research direction is to compute more interpretable policies.
So my name is Frédéric Maris, and I'm from University of Toulouse 3 in Toulouse. And I will present you the third and the last part of this tutorial on multi-agent flexible temporal epistemic and contingent planning. This part is on temporal planning, constrained and tractable classes. That is the temporal part of this tutorial. So first, we're going to talk about planning languages and what is really temporal planning. And then we'll see some algorithm for temporal planning with temporal constraints. And last, we'll see some results of complexity and some tractable classes of temporal planning. So first, I quickly remember what is planning, as said by Francois and Aurélie. Planning is a process which, given a representation of initial state, a representation of the goal, and a representation of operators, gives a solution plan. In fact, here we consider the classical planning, the classical part of planning, because in fact, here we have a solution plan, which is an organized collection of actions, while in what have been presented by Aurélie, a contingent plan can have multiple branches. So, for example, we want to make a ceramic, and from an initial state, we want to go gold and ceramic powder. We make ceramics, and then we can fire the kiln in order to have an out kiln, and then we bake the ceramics and obtain the gold by assembling the ceramics. So this is the classical frame of planning. In this frame of planning, we have instantaneous, discrete, and deterministic actions, and the world is fully observable, and there is no uncertainty. In fact, here the actions can be considered as instantaneous transitions, given that when the conditions are true in the current state, the action can be executed and then the effects becomes true. For example, here we have G1 and G2, we are positive effect, and G3 which is a negative effect. Now consider the temporal frame of planning with the same problem, that is making ceramics. Here we have the same goal, but now we consider timeline. And in fact, the action of can consider the process, which is the make ceramics, produce action. And then we are in a state now where the ceramic is no completely done. And we can continue to make the ceramic, but at the same time, we can begin the cycle of heat up of the kiln. And then we'll see that states than in the classical frame. So here we see that, for example, the process action, derivative action cycle of heat up of the kiln is executed in parallel of the action bake ceramics. In fact, here it's not. It's a little bit artificial because we could model this temporal planning problem in another way, where, for example, the cycle of each of the different actions, and then we could have a sequential plan. Even if the action have a duration, we could have a sequential plan. But it's not always the case. We'll see this later. A little bit of history of temporal planners. In fact, about 40 years ago, the first temporal planners were developed, and the first one was Divisor. In the following 15 years, two kinds of temporal planners have been developed. Some on temporal logics based on instant, and the other on temporal on interval. These as for the classical planners of this period, based on algorithm in plane spaces. Later, 15 years later, parallel to the development of other algorithms for classical planning, for example, in state spaces, and with the W. Blumenford in 1995, the same thing have been proposed for temporal planner, and probably in the same period, Satin codings for planning has been proposed, based on plan space planning instead of SAT plan, and black box for the encoding of the planning graph. So this has been extended to state spaces, to temporal extended state spaces with decision epoch planning, that is DEP. In this kind of temporal planning, the decision when to do something is taken before to decide what we are going to do at this time point. And this is this method.
Voilà toutes vos notes.
Sorry. Okay. Another kind of extended state space planning is temporally lifted planning. And here we take the decision what to do before when do the action. And this is a complete method. Other extension are plan spaces, for example, extending the temporal, the classical plan with temporal constraint. For example, simple temporal constraint with a simple temporal network, STN. Temporal constraint as DTPs, which is a disjunction of simple temporal constraints. And finally, temporal graph plan have been proposed. We'll see in the sequel how to solve temporal planning problems with this kind of. So let's take another temporal little example, which is to cook a dish of pasta. So in the initial state, we have bacon tubes, an egg, and pasta, and we want to eat a dish of pasta. It's easy to see that, for example, in lardons, breaking the egg and cooking carbonara. And then we will eat the dish of pasta. But we want to eat a dish of pasta which remains hot during 5 minutes. And here we have a little problem because it's necessary to cook the noodles and the lardon in parallel. In order to have the dish of pasta hot during 5 minutes. Okay, so this leads to two classes of temporal planning problems. The class of temporally simple planning problem, which are temporal planning problem which not require concurrency of actions. That is temporal planning problem which always admits sequential plan, and the temporal planning problems which require the concurrency of actions in order to be solved. That is temporally expressive planning problems. And this one, for these problems, all solutions require at least 2 actions in parallel. And there is no sequential plan as a solution. So the temporal framework we will consider here is based on the planning domain definition language, PDDL 2.1, where the action has a duration. The conditions of the action can occur at start, at end, or overall the duration of the action. And we will denote this by a rectangle and the precondition above and the effects under the action. The effect can occur either at start or at end. And then we can see that there are several sublevels which can be used. And for example, we will denote by a big L with an index as an index where the effects can occur, and power the condition where the condition can occur. So, for example, the condition can occur S or E, so respectively at start, overall the duration, or at end, and the effect at start or at end. So, given this notation, the temporal PDDL language is the language LSOESE, as shown at the top of the slide. So now we can give a taxonomy of temporal languages, temporal sublanguages of PDDL, given when we can define in the definition of an action the occurrence of a post-condition of a precondition, an effect or a precondition. Okay. A characterization of temporally simple language have been given by the seminal paper of Kishin Kambhampati, Mosaman Weld in 2007. What is a temporally simple language? So we'll see that a temporally simple language is a language which allows to define only temporally simple problems. That is, problems which don't require concurrency of action in order to be solved. A before condition is a condition in the definition of an action. A before condition is a condition which is defined in the timeline before an effect, before when an effect occurs, and an after condition is a condition in the definition of an action which is defined after the occurrence of an effect. And a temporal gap is a gap that is a non-empty, yes, a non-empty interval between a before condition and an effect, and an effect and after condition, or two effects. And the theorem for the seminal paper from Cushing, Kamabuti, Mozam, and Weld say that the sublanguage of PDDL is temporally simple if and only if it disallows temporal gaps. Okay, so given this theorem, we have the following taxonomy of temporal languages, which the two classes of temporally expressive and temporally simple languages. So we see that PDDL is temporally expressive and allows the definition of problems that require the concurrency of actions, while the language which was used by Divisor and all the first temporal planner was LOE, that is the language where the preconditions are defined only over all the duration of the action and the effects at end, is temporally simple. And that is the problem, because all these temporal planners were incomplete. So now let's define what is temporally. So a cyclic set of action is a set of action which define a kind of cycle in this sense. That is, for example, the action A1 produces an, which is a precondition of the action A2, which produces an effect P2, which and so on, which is a precondition of an action AN, which produces an effect Pn, which here cycle because Pn is a precondition of the action A1. Okay, so we see that in fact a cycle of action can be present in a plan and can appear in the construction of a plan, but maybe it doesn't need any other precondition at the condition produced inside the cycle, but it's difficult to determine this cycle. And the cycle may be necessary in order to achieve the goal. So a temporally cyclic plan is a plan which need a cycle in order to be solved. A cycle in the plan. Oh, sorry. A temporally cyclic problem needs a temporally cyclic plan, and a temporally cyclic plan involves the cycle of actions. So, in fact, in such a plan, deleting Pi from the effect of an action, the action AI, will invalidate the plan. That is, the cycle is necessary in the plan. Okay. For example, we want to interface two programs, and A is the action of the construction of the first program. We have Q, which are the specifications. In fact, the construction of the program produces the specifications at start. program at start. And in order to interface the two programs, we need at end of B to know the specification of A. So Q is needed at N, is a precondition at end of B. And we have the same for A. We need the preconditions P at end of A, which is the specification of the program, the second program. So now we see clearly here on this little example a cyclic set of actions. And the goal is to build the two programs to be interfaced. So namely R and S, which are produced at the beginning of A and B, respectively. So now we see the temporal cyclic, the cycle of actions, P, A, Q, B, P. And if you want to solve this problem by a forward search from the initial state, which is empty, and to achieve the goal, which is the set of R and S, we cannot execute the action A because P is not in the initial state, which is P is a condition of A, and we cannot execute B because Q is not in the initial state. So here we cannot find the goal. It's impossible to produce the goal with a forward search. And we see now why when we have a cyclic set of action, it's not always possible to find a plan by a classical algorithm with forward search. So now we want to characterize temporally cyclic languages in order to prevent this. So a temporally cyclic language is a language which allows temporally cyclic the definition of problems which allows temporally cyclic plan and which need temporally cyclic plans in order to be solved. And temporally acyclic languages are languages which allows us to define problems which always have a solution without. So we introduce a new theorem, which is a sublanguage of PDDL 2.1, is temporally cyclic if and only if it authorizes temporal gaps here between an effect and an after condition. That is a restriction of the theorem from the seminal paper of caching capability measurement Weld. And here we refine then the taxonomy of temporal languages. And in the class of temporally expressive languages, we have a subclass of temporally cyclic languages. The smallest one is LES, because here we see that in LES we have a temporal gap between an effect which is defined at start of an action and a condition which can be defined at end of the action. And also superlanguages of this language are temporally cyclic. So we see that there is a problem because PDDL now is temporally cyclic. And so that PDDL is the standard language used by all the community in order to define temporal planning problems. And so most of the planners developed earlier were unable to find some solution for temporally cyclic problem. We have seen for the little example of programs to be interfaced. But we can written in PDDL 2.1, that is LSOESE, into an equivalent problem in the language LSOSE, which is temporally expressive but not temporally cyclic. In fact, in order to do this, we will artificially cut the temporal cycles. So here we have our little running example and we want to cut, for example, the cycle by removing the precedent of the action A. So in order to do this, we will add a dummy action link check LC P for the action A, which has a P as a precondition, and this action is instantaneous here. We add linked PA in the initial state of the problem and in the goal of the problem. And we add linked PA as a precondition at start now of A, and not linked PA as an effect at start of A. And you see that when executing A can be executed when is executing A, which lead to remove linked PA, and linked PA will be produced again by link check. And as linked PA is needed in the goal, when executing A, we'll need to have link check PA. So we have to check that P is a precondition. And we'll see how to do this just after the action A. And for that, in each action, here we have only B. In each action which produces P, we add at the same time not link check active PA. And at the end of the action A, we add an action link check active PA. This link check active PA is also a precondition of the action link check. So we see that it is not possible that it's not the case that P is produced between the end of A, the action A, and the action link check. Because if this is the case, link check is destroyed at the same time as P is produced, and link check could not be executed. So this simulates the precondition at the end of action A. But here, sure, we have a restriction. That is that it's not possible to have several instances of the same action A in parallel. Okay, but this could be prevented by modeling the problem a little in a different way. So now we can, by a forward search, we can find the solution, because link PA is an initial state and is the precondition of A. To verify that, in fact, in the original problem, P is true at the end of A, sorry. And it's okay, we have a solution plan, and in order to have a solution plan of the original problem, we remove the action link check. So we have here a complete transformation with a systematic deletion of all after condition, but we can, with a more refined algorithm, remove only some of the after condition to solve the problem. And this simple algorithm has a complexity quadratic compression. So now we are going to see some methods in order to solve planning temporal problem with solvers and with temporal constraints. So why going this way? Because SAT solvers are very efficient to solve classical planning problem via SAT planning. And maybe DTP and SMT solver could be in the future more efficient and could efficiently solve, and this is already the case on some kinds of problem, to solve temporal planning problems. So we are going to see an approach which is based on the planning graph. So an expansion of the simplified planning graph, which is based on graph plan, a simple graph plan, and a floating plan extraction. Two kinds of extractions. First, the first method is based exactly on graph plan from Blumenfust. And we'll call this TLPGP1. This method is backward search conditioned by the satisfiability of a disjunctive temporal problem. And the second approach is based on the SAT planning based on black box, on the entire encoding of the planning graph into SAT, where here we will encode the planning graph into SAT modulo theory as a rational variable, the temporal aspects with the instant when an action can occur. So we are going to take another little running example, which is a temporally expressive but not cyclic example from Cushing, Kamabati, and Well, the ways. Here we have three actions, A, B, C. A has no precondition and adds a fluent A and deletes A. So A is added at start and maybe can remain on the duration of the action. This is an extension of our language, of PDD language. And A is destroyed at the end, and so on. So E and E are. So we see here that this problem is clearly temporally expressive because to execute the three actions in parallel, A, B, C in parallel, because A, B, C must occur in the plan because each one of the three actions produces one of the goals. And C, which is produced by B1, is needed by C at start. So the start of C must occur after the beginning of B. And we see that the end of C must occur before the end of A because C destroys, reproduced after has been destroyed. So we see that C is blocked between the beginning of B and the end of A. And so the three actions must occur in parallel in the solution plan. So now we're going to show, I'm going to show a method to extract a plan for this little problem, which is based on the expansion of a simplified planning graph. So at level 1, we have no initial state. We can execute A because A has no condition, has no precondition. And we add all the effects, the positive and negative effects from A at level 1. Then we make a copy of this level at level 2 and add the new possible action that is, for example, B. B is executable at level 2 because A produces the fluent little a at level 1. And so on. We expanded graph at level 3. We can execute now C, and now we see that at level 3 we obtain the three goals B, D, and E. So now we are going to try to extract a solution. We call an agenda. In fact, the agenda is given for each fluent and negation of a fluent. And in the agenda of a fluent or negation of a fluent, we will find a set of temporal interval on which the fluent or the negation of the fluent must occur or must be protected. That is, it's not the case that when an interval is in the agenda of A, for example, it's not possible that an interval in the agenda of not A overlap with this first interval. So let's begin by E. At level 3, we want to state that E. So it's possible to take, for example, the action C, and we add to the agenda of E that we have the causal link from toStart. So toStart is the instant when C start at level 3. toStart C3 plus 1. Because E is produced one time after the beginning of the action C. And until the goal, TOG is a special temporal instant when we want that the goal is true. And on all this interval, E must be protected. That is, not E cannot occur. And we add, so here we have the causal link in blue. And in black, we have a singleton here, which could be an interval, which is the side effect, not B, which is produced by C at toStart of C3 plus 1. So now we have to produce all the precondition of C, that is only one here, little c, and we select, for example, one action at the first level, at the previous level, which produces a C for C. For example, here we take a B at level 2, B2, which produces the fluency for the action C at level 3. That is a causal link. We select the causal link. So we had a constraint that C must be produced before three, and we had in blue in the agenda of C the causal link that C must remain from the start of B2 to the start of C3, and all the side effects. And now we see that, for example, we have added intervals in the agenda of C and in the agenda of not C. And so separate this interval. So we have to add constraint here. We had a constraint that toStart of C3 is strictly lesser than toStart of B2 plus 4. And in fact, here we have simplified the disjunctive, because here we could have, which is the end of an interval is before the beginning of the other, and conversely in the other side. So we continue. For example, here A produces little a for B. We have the constraint that A is before B, and we update the agenda. Now we update the constraint because of the conflict between the agenda of a fluent and its negation. Then now we want to produce the second goal D, and D is already in the plan, produced by B at level 2. So to agenda of D, the protection of the causal link, and add the constraint of separation of intervals, and so on. We do the same for little b, and now we just have to call the constraint solver. Sure, we call the constraint solver at each time we add a constraint, because we can prune the research and backtrack, in fact. And here we have the solver will give us, we have the action in the floating plan, which are the selected action A, B, C. And the constraint solver will give us time point when the action must occur. That is values for the temporal variables. But we have also one of the constraint from the disjunct, which is selected. And so we can have, with this characteristic instant ordered, a scheduling for the temporal plan. And sure, there are other possible scheduling, which could be given by the constraint solver. And finally, we have a floating solution plan. Here, for example, the make span of this plan is between five steps from 8 steps. And given that when you execute A, for example, during the execution of A, the beginning of B or C, respecting the constraint, the temporal constraint given here by the lines. So there is another possibility, that is the encoding of the whole temporal planning graph into SAT modular theory, but yes, we don't have many time here. Maybe I can explain this and print the end of the presentation. So for example, here we have 4 rules for encode the entire planning graph. The first rule is to have, for example, 2 dummy nodes for the initial state and the goal. So these nodes of the planning graph are true, and the node initial will produce all the initial state, or the fluent of the initial state, and the node goal will need all the fluent from the goal. The nodes corresponds to actions in the plan, but here these 2 actions are dummy actions. The second rules say that when for each precondition arcs in the plan, that is arcs from a fluent to an action, if the action node is true, is selected in the plan, then there exists a causal link from an action which produces P for the action B. Okay, here we can see this. In fact, in the graph, we have a node action at a previous level which produces the fluent P for the action node B. After we activate the actions and define a partial order between the action. If a causal link is defined in the plan from an action A which produces P for an action B, so from a node of the node for action A to the node of action B, that is that the node of A is true and the node of of B is true. So the action A and the action B are selected in the plan. The instant when P begins to be produced by the action A is before the instant when the action B needs the fluent P. And finally, we exclude the contradictions between the execution of actions and we prevent the deletion of a fluent during a causal link. So first, during a causal link, when a causal link is defined from the action A which produces P for B, and when an action C in the plan, we need to define that the instant when C destroy P is strictly before the instant when A begins to produces P, or this is a disjunctive constraint, or the instant when C destroys begins to destroy P is strictly after the instant when B finishes to need P. And finally, for the side effects, when we have two actions A and B, which are contradictory effects, A produces P and B destroys P. It's not the case that A and B can produce and destroy this on the same interval. So the instant when B finishes to destroy P is before the instant when A begins to produce P, or the instant when A finishes to produce P is strictly before the instant when B begins to destroy P. So, and this could be seen, but if you're interested, maybe you can exchange with us and send me an email, or we can see that later. But we have developed a tool which is Twist, and we can encode this kind of problem into propositional logic, and with, for example, quantifier free reference logic with that modular theory solver, we can solve this kind of problem. Here we have a little problem, the gripper, which is a robot. We have to move balls from a room to another, and here we see that the solver gives a solution. So maybe now it's already time for this tutorial to see the third part of this third part of the tutorial. Complexity and tractable classes of temporal planning, but I think it's not necessary to go on this, because maybe another time. I think we've seen an overview of temporal planning with temporal with algorithms using temporal constraints in order to solve a temporal planning problem, temporal languages. So maybe another time for tractable classes. And so what I wanted to say is some words on perspectives of MAFTEC planning. Here we have presented some part of some aspects of different aspects of planning. For example, epistemic with Francois, contingent and multi-agent planning with Aurélie, flexible and temporal as that I just presented. But some combination of these aspects have been already done. But now we want to push further this combination, and maybe we will propose a workshop on this on a future conference or other things like this. We already proposed a workshop, but due to the pandemic, it was cancelled, and now I hope that it will be possible to work again on this combination of different aspects more further. So, for example, with temporal and epistemic pushed together the two aspects, but maybe the important part would be to work on the knowledge of on the time, know when something is happening. For now, we just have the temporal aspect and the epistemic aspect together, but without really something like I know that the other agent knows when I will know something. So thank you very much.